So hello everyone. Thank you very much to the organisers for inviting me. It's extremely nice to be back out and see people in person. It's been quite a long time. I'm going to talk a little bit basically about growth and characterisation. I've changed this a little bit from the title before because it's actually swapped to manganese telluride quite a lot in the last month. So I should say I haven't put any names on there. I'm Peter WADLEY. I'm an associate professor from the University of Nottingham. But basically, once I start including all of the collaborators, it's a lot of people here. So I've just put the three main institutes. So for me, this, I don't know if that's a bit loud. It's okay. For me, this feels, I don't know if it's just for me, but kind of nostalgic. So almost 10 years ago, I was preparing a talk that felt very similar, very heavy on material characterization, on techniques. And I think this will be of interest to some of the experimentalists here, less so maybe to the theorists. But at that time, there was just emerging predictions of spin textures within the unit cell, subunit cell level. And it felt like a very significant time. And a couple of years ago now, I think, is when I first started hearing discussions of altermagnetism. And it feels similarly momentous. And personally, I'm in a similar place, but also it's a really exciting time, I think, to be in this field. So this is just a blast from the past. So nearly 10 years ago, this was the first measurements of that predicted, well, the use of this predicted spin texture in the dynamic sense. So the first measurements of the NSUT that we made back in 2014, the end of 2014. And then since then, we've come a long way. And a lot of people, I've listed basically papers that I've been involved with, but this field has been driven forward by a lot of the people in this room. And we've really gone from the situation where antiferromagnets seemed almost, or fully compensated systems seemed almost impossible to control to a scenario where we're, at least in terms of control, somewhere closer to where ferromagnets were. And in addition to that, we've approached the fundamental limits of switching, both in terms of speed and efficiency. So it's come a long way. So I'm hoping the same for the altermagnets. Maybe in less time. So, and still sticking on the antiferromagnets, so this came out yesterday. We're still doing some work on this. And this is generation and control of vortices in copper manganese arsenide. So there's still some really nice stuff going on the antiferromagnets, but I've kind of shown this because at the same time, when these discussions started 2 years ago about the altermagnets, a lot of retooling was necessary in Nottingham to start looking at these systems. I'm just going to highlight my postdoc and PhD student, Ollie and Alfred. They've been working incredibly hard for the last year or so or two on the characterization, but also the last week up until Friday, where a lot of the data that's going to come later was put in, and over the weekend as well. I should say, an excuse up front, some of the data is pretty raw, so I'm going to take it with a pinch of salt. I welcome questions at any point because it's it's quite fresh. I think it's fair. Okay, so altermagnetism. So after these discussions, obviously a couple of years ago, I think the discussion started. This is the more recent PRX. But at that time, I started thinking about how to get into this new field. So Dominic has kindly gone through this in a lot of detail, and obviously Libor as well. But we're looking for this third class, this altermagnetic class, with the spin split band structure. So immediately, it's a funny concept for an experimentalist when you start thinking about shuffling through material systems, not based on small variations of something you know, but really changing the elements based just on symmetry and topology. So I kind of figured at that point that we need, at least at Nottingham, we needed a different setup. And it's interesting that many places have kind of converged to the same setup. So connected growth and characterization, where you can go through a lot of systems. In the meantime, we wanted something to do, so we looked at the list of predicted materials. And for us, these two are the ones that are accessible in our current Gen 3 machine. So we grow most of the stuff by molecular epitaxy. This was the copper manganese arsenide machine. And these two we can do with very little modification, so that's where we started. The band structure particularly from the point of view of the spin split R pairs, looked incredibly interesting. And we started on the chromium antimony. I think it was nearly 2 years ago now. So we followed a paper actually, I think in York, from a few years ago where they had grown chromium antimony on gallium arsenide 111 with a buffer layer of manganese antimony. And this actually appears to grow really nicely. You can see the XRD here, so you can see clearly the chromium antimony 002 and 004 peaks, and next to it the manganese antimony. And if you look in plane, you can see that it's a well-ordered single crystal with the expected six-fold symmetry. What was a little surprising is the read looked perfect, but so the surface diffraction looked perfect, the growth looked really well, but when you take it out, it's immediately milky and opalescent, which is not a great sign. This?
No, the small ones.
Here?
No, next to manganese antimony, 002.
In the middle.
Here?
Yeah.
I'm actually not sure.
Maybe
But there's I don't think so, because I'll come to that later. But it's certainly, I ran a very long scan, they're very weak. They didn't concern me too much, but I don't know exactly what they are. It could be associated with this, which is actually something I didn't want there. It's the substrate has a contingent of 115 for some reason. It's a 111 substrate, but there must have been something in the melt. Yeah. No, the answer to the milkiness becomes clear once you start doing AFM. So the layers that I just showed the XRD on are closer to this one there with the buffer layer of manganese telluride. And what we find are that you get incredibly, very flat-topped mesas, but with trenches separating them with a range of widths. And I think that's where the optical scattering comes in and gives you this pearly, opalescent look. You can grow it actually with no buffer layer at all, and you get from XRD a pretty comparable crystal quality. But you can see that the mesas are much smaller. The whole intention of this was to get it to ARPES as soon as possible, spin resolved ARPES, and try and show this large predicted band splitting that Libor showed. I won't give any spoilers, but it didn't work. So if we look in a bit more detail, wider out at the atomic force microscopy, you can see that you have these flat-top mesas with slightly varying heights. These trenches actually go right the way down to the substrate, so they're inherent in the buffer layer as well. More nice pictures of these hexagonal structures. So that's where I'm going to conclude the chromium antimony bit for the time being. And the reason for that is that we attempted a couple of times to take it to the synchrotron, namely Electra. The surfaces were really problematic. We maybe can have a better go at it now, but we tried arsenic capping, decapping. After very aggressive heating in our lab-based ARPES, we did start to see hexagonal band structure that looks quite nice. I am not sure whether that is the layer or the substrate. We're worried about that. But the reason that we've taken a break from it is two reasons, really. Laterally, it's not conductive, so it's poor for magnetotransport, even though you can't really expect much from the magnetotransport without some form of symmetry breaking. But the main reason was it appears to be destructive, at least in our MBE system. So it completely destroyed the shutters to its cell. It also destroyed the mass spec. And so Richard Campion, who grows the layers, is really not keen on it. But we will return to it. But in the meantime, we decided to replicate the manganese telluride growths that Dominic's just talked about and the Linz ones in the effort to have something to do while we develop the new systems. These grew incredibly well. So for me, they were the best looking XRD and AFM that I've seen on a thin film layer. I think I've put the text in the wrong place. So the rocking curve, you have these nice thickness fringes. On almost every layer, they grow impeccably well. They have an interesting morphology on the surface. You'd be forgiven for thinking these are pyramids. They are kind of pyramidal, but the slope is actually 2.5 degrees. So they span huge distances. And in fact, you get flat regions like this region here, where basically 400 nanometers, it's completely flat. So this looked a lot nicer to us. And we started to do the magnetotransport. And although in many ways, well, in most ways, we're just repeating what Dominic's done. There's nothing quite like actually seeing the size of this effect and the memory of it. It's really interesting to see it in reality. So one of the things I'd like to point out here, because there's been quite a lot of discussion about this effect and relating it to ferromagnetism, here, and this is somewhat with a pinch of salt, you'll see the axes are in slightly different units, but actually they're just out by 100, so they're in ohm centimeters. It appears to be 10 times the size of the ones published in the PRL. But I think the most, I will come back to that, but I think the most significant point is the width of the coercive broadening. So here we have a 7 Tesla. The energy barrier between the two states must be really quite large. And I think this is probably because we seem to have very large, at least crystalline domains, and I suspect probably magnetic ones, in the Hall domains. So luckily Dominic covered this in a lot of detail because I haven't put the diagrams, but I would point out again that this domain is the Hall domain. So this is Dominic emphasized it with an exaggerated canting between the two sublattices. Yeah, this is astounding to me. I mean, it shows up so clearly in the magnetotransport. The other thing to note is that at remnants, we have basically 100% saturation. So we can set that state, and one of the questions that I think that came up about Dominic's one was the minor loops. So this was all done last week, so it's not done in a lot of detail. But what we did do is heat up to 270. 270 is as far as we got while sat on both of these positions. Unfortunately, the heater broke at 270. But on returning to this temperature after a heat to 270, you retain the full memory of the state. So that's even above, if you can remember, and I think I've got some graphs to show you, but if you can remember where the zero field warm-up in Dominic's curve disappeared, I don't know, about 240 or something. Actually, the memory of it persists longer, at least in our case.
That is a minor, right?
Yeah.
That's not saturated yet. It's pinched it, so that's a minor loop itself. A minor loop.
So it's not fully saturated, probably, because...
Probably not. 6 Tesla is as far as we can go, and it's fairly linear at that point, but it's incredibly raw. Yeah.
Did you do any magnetometry on these to see?
And not on this layer. This is literally from last week. Yeah. The last measurements were on Thursday.
Did you make this?
This was at 150 Kelvin.
No. When you grow the sample.
Oh, I see. That's a good question. I think it's basically around where it's a slightly complicated answer because we grew it on a different holder, at least some of it. And we used the oxidation removal temperature, but it's in the range that's stated in Dominic's paper, which I think is about 370 to 420. It's somewhere in that range. Yeah.
So, maybe you mentioned that, but if you did, I missed it. That magnetization is along Z here.
Yeah.
And if it's along Z, then there shouldn't be any anomalous Hall effect by symmetry.
No. This is.
Main vector along Z would not allow.
Yeah. No.
Yeah, right. But from antimony should be.
This is manganese telluride. This is manganese telluride. Yeah. No, I'm sorry, I switched. I ended the chromium antimony. I don't blame him.
Can we go get it back and repeat the growth of manganese?
I don't think anyone wants that.
You said that you didn't have enough slides.
Yeah, I probably don't. But I'm happy to stay here if there's more questions.
Did you subtract any?
The ordinary Hall. Yeah. And obviously, I mean, as you will know, we can't go out far enough to fully saturate, so this is slightly a guess. Yeah. And it's based a bit more on the shape on the top of the curve. We've also subtracted an even component like Dominic does in the paper. Yeah. And I mean, to first glance, that subtraction, it's just those two things, the linear slope and the even component, and you get this, which looks, at least somewhat believable. I would love to go out another 5 Tesla, which we will do. We will do in a week or two, actually. Yeah, so I'll update you. But, and in principle, so this hasn't been evened out as nicely, but this is the one where the heater broke, but we managed to heat up to 270, come back. So It seems to remember to at least 270. I'd like to know exactly how far that goes.
Do you have any idea where carriers are coming from?
It's a good question, and I really want to sit with Dominic and compare some of our values. In our system, it's been used obviously for copper manganese arsenide. There is a background of arsenic. It's quite possible that arsenic would be an unintentional p-type dopant. Yeah. So it might be that, but it's only a guess at this stage. We will look at it in more detail. And this is one of the last bits of experimental data which I find really nice, and it's essentially, this is literally the last thing on Friday, but it's two different devices, and it was field cooled in 0.3 Tesla, so really quite a low field across the transition. And this is just the warm-up. And so it's a warm-up after a positive field and after a negative field, and this is just the average of the two sets. So obviously you have other things like the RVT on that, but what you can see really nicely is this convergence of the anomalous Hall component. And because of the way the RXX is mixing in, the sign is reversed between the two. But actually, I didn't remove the average because it just symmetricizes the whole data set and it looks horrible. But if you do that, they fit over each other incredibly well. So the anomalous Hall is just there. You can set it with 0.3 Tesla, and you can see it up to, there's some doubt in the X calibration. I have to do a little bit of work on that. But up to some temperature, you just see the anomalous Hall, and then it disappears, but I think it disappears before the actual domains are forgotten. So in parallel on Friday, we were also taking ARPES data.
But what about Monday? This is disappointing.
I had to try and write this.
Today's Tuesday. Tell me on Monday.
What are they doing right now?
Preparing to redo this, actually. And I'll explain why. So when we got this in, I've got quite a bit of experimental kit that I wanted to show if we have time, but I've moved it to the end. But at Nottingham, we've just have this freshly commissioned Nano ESCA setup that includes an Omicron ARPES, as well as in situ STM and MBE growth. This was transferred in vacuum suitcase, but the vacuum suitcase was assembled and pumped down for 2 hours, which meant there was a bit much water in there. At the beginning of this experiment, we saw no structure whatsoever. After heating to 70 K for a couple of hours, you start to see the hexagonal constant energy slices that you'd expect. And even we can get a little bit of band dispersion out of it. It's a multi-user facility. They wouldn't let me heat to 100 because they were worried about arsenic contamination, this is just therapy at this point. I'm incredibly frustrated about it. We'll repeat it next week with a drier suit. And I expect a really large improvement on the band structure data. So I tried to get the workshop delayed by 2 weeks, but I will have to come back to you with the data. But I think already next week we will have much nicer data. Yeah, the conclusions are basically already discussed. Together with Dominic and the rest of the people working on manganese telluride in Czech Republic, we have beam times in May and June, so we will look at XMCD, at beam. All of the nice stuff I wish I could have included in the book we should have soon, and in June we'll return to Electra with both the chromium, antimony and manganese telluride, and I hope to be able to update you guys after that. So, I don't know, we don't have time, I guess.
Yeah,
we have time. So that's the end of the experimental bit. So if there are any additional questions that people want to ask now, that's fine. And the rest of it, I was just going to run down what we have in the lab, which is less interesting. But
I don't understand. Are you done with your talk?
I'm asking for a time. I'm confused too. How are we for time?
1 minute, 2 minutes?
Yeah, 1 minute. Just 1 minute. Yeah. Yeah. So I think this is because I'm experimental. I just wanted to say a bit about the retooling that we've done and what we have at Nottingham now, because I think for future collaborations or anyone who wants to come, experimentally, it's maybe of interest. So the Gen 3 was our main workhorse machine. It has 12 ports, including 2 retractable ones. And that has been also transition elements. So the copper manganese arsenide, the manganese telluride, and the chromium antimony were all grown on this MB system. In the meantime, I say we, it's a royal we, Richard has designed and had built a new oxide MB chamber. Yeah, that's Richard. He's blockier than he used to be. Yeah. So here we have 8 growth cells, including a catalytic oxygen source. So this gives us a much better access to some of the predicted materials, the ruthenium dioxide, the hematite, and many others. In addition to that, the NanoESCA, which I just said we used, we have a custom vacuum suitcase and also a custom holder for the MBE system so that we can go directly. This is James O'Shea, who took the measurements last week, and Sabrina, his PhD student. We can take samples directly into this NanoESCA setup and do vacuum STM RPES. And also, with Philip Moriarty, we have connection to this spin-polarized Unisoco high-field SPM. So this has all just come online recently, and they have some pretty amazing capabilities. So Brian Kirali, who moved to Nottingham a year and a half ago, has made like atomic scale electron cages. So we are thinking even about making artificial 2D magnets using cages for single electrons. I'm not going to talk about that. And lastly, we have also a full field of ecomagnetics microscope, this is cryostat, 8 standard electrical feed-throughs. We've also built 2 4-port mini chambers for some of the riskier materials. So we really can go through quite a lot of, for those theorists who think we should look at some particular material, we're starting to be able to access quite a lot of them, or will be able to in the coming year. I think that's it. Thank you.